Alright, starting a new one. This one's Unit 4 in the Hugging Face Deep RL course. This is a read-through, kind of study with me style. I'm literally just going to read the course. So, if you're interested in that, this is the introduction to Policy Gradient with PyTorch. In the last unit, we learned about deep Q learning. In this value-based deep reinforcement learning algorithm, we use the deep neural network to approximate the different Q values for each possible action at a state. Since the beginning of the course, we only studied value-based methods, where we estimate a value function as an intermediate step towards finding an optimal policy. So here we have an equation, the link between value and policy. Finding an optimal value function leads to having an optimal policy. That's what we did in Units 2 and 3, where Unit 2 we had the Q table, Unit 3 we replaced the Q table with the neural network, and it looks like we're going to do something different. Now, in value-based methods, the policy pi only exists because of the action value estimates, since the policy is just a function. For instance, a greedy policy that will select the action with the highest value given a state. But with policy-based methods, we want to optimize the policy directly without having an intermediate step of learning a value function. So today, we'll learn about policy-based methods and study a subset of these called policy gradient. Then we'll implement our first policy gradient algorithm called Monte Carlo Reinforce from scratch using PyTorch. Then we'll test its robustness using the Cartpole v1 and Pixelcopter environments. You'll then be able to iterate and improve this implementation for more advanced environments. So this is Cartpole. You have a cart, there's a pole, you gotta balance it, and I believe this is Pixelcopter, or this is a helicopter. Let's get started. What are policy-based methods? The main goal of reinforcement learning is to find the optimal policy pi star that will maximize the expected cumulative reward. Because reinforcement learning is based on the reward hypothesis, all goals can be described as the maximization of the expected cumulative reward. For instance, in a soccer game, where you're going to train the agents into units, the goal is to win the game. We can describe this goal in reinforcement learning as maximizing the number of goals scored when the ball crosses the goal line into your opponent's soccer goal, and minimizing the number of goals in your soccer goals. Okay, I think what he's trying to get at here is that in reinforcement learning, we're trying to maximize cumulative reward. So there's like one scalar value that we're trying to optimize for, and when we're given the reward, it can be negative or positive, right? And somebody scoring on your goal versus a goal that you're scoring, these are negative and positives that eventually accumulate into a single scalar value. I think that's what he's trying to get at there. Value-based, policy-based, and actor-critic methods. So these are three different. We studied in the first unit that we have two methods to find, most of the time, approximate this optimal policy pi star. In value-based methods, we learn a value function. The idea is that an optimal value function leads to an optimal policy pi star. Our objective is to minimize the loss between the predicted and target value to approximate the true action value function. Minimize the loss meaning we're trying to get our Q table or our Q neural network to be more accurate. We have a policy, but it's implicit since it was generated directly from the value function. For instance, in Q learning, we defined an epsilon greedy policy. On the other hand, in policy-based methods, we directly learn to approximate pi star without having to learn a value function. The idea is to parameterize the policy. For instance, using a neural network, pi theta, this policy will output a probability distribution over actions, a stochastic policy. So here's a stochastic policy, here's a probability distribution. The policy given a state outputs a probability distribution over actions at that state. So here's the probability distribution, here's action given the state, parameterized by theta. Our objective then is to maximize the performance of the parameterized policy using gradient ascent. To do that, we control the parameter theta that will affect the distribution of actions over the state. over a state. So this is parameterized stochastic policy. The state is, for this one, it's carpal. The state is different attributes like position, velocity, pole angle, pole angular velocity. That goes into an input layer. There's a fully connected layer here, and this is the parameterized policy. Here's a softmax over these actions. Here we only have push left and push right, and these are the probabilities. Finally, we'll study the next time actor-critic, which is a combination of value-based and policy-based methods. Okay, great. Consequently, thanks to policy-based methods, we can directly optimize our policy pi to output a probability distribution over actions that lead to the best cumulative return. To do that, we define an objective function, j, that is the expected cumulative reward. And we want to find theta that maximizes this objective function. Okay, so that's a lot of words, but basically we're going to have a function that takes parameters. We want to optimize those parameters to, maximize expected cumulative reward. The difference between policy-based and policy gradient methods. So policy gradient methods, what we're going to study in this unit, is a subclass of policy-based methods. In policy-based methods, the optimization is most of the time on policy, since for each update we only use data, trajectories, collected by our most recent version of pi. The difference between these two methods lies in how we optimize the parameter. In policy-based methods, we search directly for the optimal policy. We can optimize the parameter data indirectly by maximizing the local approximation of the objective function with techniques like hill climbing, simulated annealing, or evolution strategies. In policy gradient methods, because it is a subclass of the policy-based methods, we search directly for the optimal policy, but we optimize the parameter theta directly by performing the gradient ascent on the performance of the objective function. Before diving more into how policy gradient methods work, the objective function, policy gradient theorem, gradient ascent, let's study the advantages and disadvantages of policy-based methods.